Hello and welcome to Bedroom Physics. This is the example video for the Newtonian mechanics. I'm going to be doing two examples. They're both pretty similar. One is a system like this, except the rope has a mass, and the other one is a system like that, but the rope does not have a mass. So let's get started. Our system that we have here, we have a force being exerted on a mass A, which is connected to a rope, which is connected to a mass B, and we want to solve for the acceleration of the entire system. We want to solve for the tension at the top of the rope, and we want to solve for the tension in the midpoint of the rope, and we want to solve for the tension at the bottom of the rope. So in order to do this, I like to break it up into three different parts because there are three different bodies, and create free body diagrams for each of them. So for my mass A, I have my force being exerted on mass A, I have the force of gravity being exerted on mass A, and I have the force that the rope is exerting on mass A. On the rope itself, we have the force of gravity that's being exerted on the rope. We have the force that mass A is exerting on the rope, and we have the force that mass B is exerting on the rope. And lastly, we have mass B, and the force of gravity is being exerted on mass B, and also the force that the rope exerts on mass B is here as well. From these free body diagrams, we can derive that for our mass A, we have our force plus the force that the rope exerts on mass A plus the force that gravity exerts on mass A, and it's going to be equal to the mass of A times the acceleration of the system. For our rope, I have the force that A exerts on the rope, plus the force that B exerts on the rope, plus the force that gravity exerts on the rope, and it's going to be equal to the mass of the rope times the acceleration of the system. We have the force of the rope on B plus the force of gravity on B, and it's going to be equal to the mass of B times the acceleration of the system. And lastly, we have the force plus the force of gravity on all the bodies, and it's going to be equal to the acceleration of the system times the masses of all the bodies. Okay, so we want to solve for A. If we look at the first formula, we'll see that we have an unknown here. We don't know R of A. For the second formula, we don't know B of R, F of BR. And for the third formula, we don't know F of RB. But on the fourth formula, we don't have any unknowns, and it actually also involves A. So we'll use this one to solve for A. So F plus G MA plus MB plus MR over MA plus MB plus MR is going to be equal to 3.28 meters per second squared. And again, that's going to be the force, which is 170 newtons, plus the force of gravity, which is going to be negative 9.8 meters per second squared, times 3, which is mass of A, plus 3, which is the mass of the rope, plus 7, which is the mass of B, over M of A, which is 3 kilograms, plus M of B, which is 7 kilograms, plus M of the rope, which is again 3 kilograms, and it's going to give us 3.28 meters per second. Now that we have the acceleration of the system, we can start solving for the tension on the rope. So the tension on the top of the rope is F of R of A. As you can see here, I'll be using F of A of R and T of A of R interchangeably. They pretty much mean the same thing. So if we solve for F of R of A, we will know F of A of R because F of R of A is equal to negative F of A of R, because it's a body A exerting a force on body B and body B exerting a force on body A, which means they're equal in magnitude but opposite in direction. So if we want to solve for, we'll have M of A minus M of AG minus F. So this is going to be 3 kilograms times 3.28 meters per second squared minus 3 kilograms times negative 9.8 meters per second squared minus 170 newtons, and it's going to be equal to negative 130.8 newtons. And since this is equal to F of R of A, this is going to mean that F of A R, which is equal to T of A R, is going to be equal positive 130.8 newtons. And now we can solve for the bottom, and that's just going to be M of B of A minus MBG is equal to F of RB. So again, this is going to be the mass of B, which is 7 kilograms, times the acceleration of the system, which is 3.28 meters per second, minus the mass of B, which is 7 kilograms, times the acceleration of gravity, which is negative 9.8 meters per second, and it's going to be equal to 91.6 newtons. And since we're looking for the tension of B of R, which is the force of B of R, it's going to mean that the tension of B of R is equal to negative 91.6 newtons. And remember, the negative just represents a direction. It doesn't actually represent any sort of magnitude wise. The magnitude is 91.6. It's just a direction. In this case is going to be downwards. And lastly, to solve for the midpoint of the rope, we'll be using this formula here, but we're going to have to change it a little bit because we're only looking at the midpoint of the rope. So it's only going to be half of the mass. It's not going to be the full mass. It's not going to be 3 kilograms. It's going to be 1.5 kilograms. And this force here, the force of B of R, is actually going to be the force of B on the rope and also the force of the second half on the rope on the rope. So we'll actually have to divide these masses by 2, and this is going to be an unknown. Okay, so M of the rope times the acceleration of the system minus, and it's actually M2 minus MR over 2G, but F of A of R is going to be the same because it's above the half, so this force of A is still being exerted on the top half of the rope. Minus F of AR. This is getting a little, I'm going to take it over here. So M R to A minus M R to G minus F of AR is equal to some unknown F. Let's call it F2. And that's going to be equal to negative 111.2 newtons. And again, the negative just represents a direction. Okay, now on to the second problem. Okay, so for this problem, we have two masses, mass A, mass B. We have a light, or aka massless rope with a tension of 41 newtons. We have a force being exerted on mass A for 100 newtons. And we know that the bodies travel 14 meters downwards in 5 seconds. So what we want to solve for is mass A and mass B, and we also want to know the acceleration of the system. Alright, first let's draw some free body diagrams. I have here the mass A. There's a force being exerted on mass A of 100 newtons. The force of gravity is being exerted on mass A, and the force that the rope exerts on mass A is here. And we have the mass B free body diagram, which is the force of the rope that is being exerted on B, and the force of gravity that is being exerted on B. I didn't do the one for the rope because the mass is 0, so it's pretty much just going to be equal 0, but I have the formula here. F of AR plus F of BR, it would have been plus the mass of the rope times gravity is equal to the mass of the rope times the acceleration, but the mass of the rope times gravity and the mass of the rope times the acceleration both go to 0. But let's start at the very top. For free body diagram for body A, we have the force plus the mass of A times gravity plus the force that the rope exerts on A, and it's going to be equal to the mass of A times the acceleration of the system. we have the force that the rope exerts on B for this free body diagram, plus the mass of B times gravity. It's going to be equal to mass of B times the acceleration of the system. Again, we have the formula for the rope, but I've made a change. I've only subtracted this, and it's going to be F of AR is equal to negative F of BR, and negative F of BR is equal to F of RB anyway. And that's going to be equal to 41 newtons, which is our tension. And we also have F plus the gravity that's being exerted on both bodies is equal to the acceleration of the system times the mass of both bodies. And we have change in Y is equal 1/2 A times T squared. This is from single dimensional motion. And considering I've already subtracted Y initial over, and we don't have an initial velocity. The initial velocity is just 0. So all we're left with is 1/2 A T squared. So let's solve for that really quickly. So change in Y times 2 over T squared equals A, and that's going to be negative 14 meters times 2 over 5 squared, so 25 seconds squared, and that's going to be equal to negative 1.12 meters per second squared. Okay, so now that we know the acceleration of the system, we can solve for, let me see what we can solve for. We can solve for both of them. So let's solve for B, and then let's solve for A. Okay, so if we want to solve for mass B, we're gonna have to isolate B, and we're gonna do that by moving it over, extracting B, and then dividing the rest of it. So we're gonna get F of R B is equal to MBA minus MBG is equal to MBA minus G, which we will transform to F of R B over A minus G equals MB, and it's going to be equal to 4.72 kilograms. And we could probably also solve for A. Do I know F of RA? I guess I do. So it's going to be the same thing. We're going to want to isolate A and then divide the rest of it. So we're going to add F plus F of RA is equal to MA acceleration minus MA gravity, which is equal to MAA minus G, which we will transform to F plus F of RA over A minus G, which is going to be equal to 6.8 kilograms. And remember, F of RA is going to be negative 41 newtons because F of AR is equal to positive 41 newtons. Our F is just 100 newtons, our A is the acceleration that we solved for, and our G is going to be gravity, but it's minus gravity, so it's actually going to be plus 9.8 meters per second squared. In any case, this has been the example video for Newtonian mechanics. Hope to see you in the next concept video. I believe it is more applications of Newtonian mechanics. Thanks for watching.